Okay, this is example 4, and what we're going to do here is another little problem. And what we have here is several remote networks hooked together. In this case, there are 10 remote routers, router 1, router 2, and then we do the dot 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 dot, showing you the network would look essentially the same all the way out to router 10, remote 10. It doesn't. We don't need to draw the other ones because they're not going to be pertinent to the problem. And we've been given a 192.168.4.0 and a subnet mask of 255.255.255.0. And this remote or this sort of branch office design only has about 5 PCs at each site. And it looks like we have 19 networks to support here. As you see, I've numbered them. So network 1 will be subnetwork 1, network 2 will be subnetwork 3, and so on and so forth. Now, looking at the problem up here, given that the router uses the first usable address of each subnet, meaning that the, let's say, the FA Fast Ethernet 0, FA0 interface of remote 1 would use the first available address on network 1. So given that information, it's going to be the same for network 3 and so forth. And for network 2, we'll just say that the router on the right hand side will use the first address, the router on the left hand side will use the second address. So given that remote 1 uses the first usable subnet and so on for subsequent routers, the question is, what is the interface addresses for remote 1 and remote 10, and what are the host addresses for remote 10? So we want to know what both addresses, the FA0 interface address is, the S0 interface is on network 2, and we want to know what the FA0 interface is here on remote 10, and we want to know what addresses all 5 PCs will use out here on network 19 off of remote 10. That's really what the question is asking. If you don't see that, go ahead and stop here and keep looking through it until you get it. And based on that, let's go solve the problem. So the base address was 192.168.4.0, and the subnet mask was 255.255.255.0. As you can see, I've already thrown out network 0 here. And the first usable network will be 0, 0, 0, 1. And we set our host bits to 0 when we're determining that. And we come up with 192.168.4 dot what? Well, let's look at our number line. And we see that it's 4.8 is the network address. Now, how did I get the number line here to start? How did I get the divided line here all the way down to the 5th bit, by the way, or the 5 bits worth of subnets, by the way? Remember, we borrow the number of bits we need to make the number of networks we need. In this case, we needed 19. Remember, 2 to the 4th is 16 minus 2 is 14. 14 networks would have been insufficient. So we borrowed 5 bits. 5 bits. 2 to the 5th is 32 minus 2 is 30. So 30 networks is large enough to support 19. So we'll have, 11 spares or so. But we needed at least 5 bits. So 0001.000, that is the network address. And the subnet mask will be, remember, you got 5 ones here now to be network bits in the 4th octet. So the new subnet mask is 255.255.255, and the last octet will now be, that would be 128, 192, 224, 240, 248. All ones in these first 5 bits would be 248. So the new subnet mask is now this guy here. Alright, the first host address on this first network would be 001 in the host bits, and of course this is the network address we're dealing with, so it would be 192.168.4.0. 4.9. Now just to solve out the first network all the way, let's just go ahead and say we would continue on down until 110 were reached, and that is the last host on that subnet. And that last host is 4 dot what? Well, 6 plus 8 over here is 14, right? So 14. Now how many hosts are we able to support here? Well, we got 3 bits. So 2 to the third is 8 minus 2 is 8, and then you got to subtract 2. So 8 minus 2 is 6. So we can support 6 hosts per subnet. And that looks right. That's like a 6 range here. 9 would make 1, 10, 2, 11, 3, 12, 4, 13, 5, and 14 would make 6. Oh, and by the way, I forgot the broadcast address. That would be 111, and that would be .15, and it would also be part of that first network range. Let's make another line here then. Okay, the next network would be 00010. Just as easy as that. I mean, you're just simply counting up 1 in binary, right? And the host bits would be zeros while we're determining the network address. That would be 192.168.4.16. That makes sense because the increment is 8 between the first and second network. That makes sense. And the first host address would simply be 001, which would be .17, correct? Then, of course, we would go over here and we would apply those addresses. This would be .9, 192.168.4.9, and this would be 192.168.4.17. And incidentally, this would have been the next in sequence, been .18, because it's also in network 2, the serial interface for remote 2. The other serial interface remote 2 would be in another network. And it's not in network 18. This just simply means we're continuing on down in a router chain, remote 3, 4, 5, and 6, and so on, until we got to remote 10. So we're not going to worry about this over here for now. But .18 would have been over here, .17 over on this router, router 1, remote 1. And that would have been how we apply the interfaces on those routers. Now, going back to the diagram, it asks us also what is the interface, what are the interfaces for remote 10? And remote 10 happens to have its serial interface in network 18 and its Ethernet address in network 19. And we are going in order by the networks here, 1, 2, 3, and so on. So it would simply go 18 to 19 to solve these problems. So we need to find out which network is network 18 and which network is network 19. Now, the way of doing this is to simply count in binary to network 18. Now, how would we do that? After all, the number line starts over here at 1. How would we get to 19? Well, for a while, pretend the host bits aren't there. Just pretend this part of the world doesn't exist, and pretend this is the only numbers we're worried about. All we have to do is get this binary number to 19, and what we'll do in the meantime is we'll reset our number line at 1 here instead of 8, and 2, and 4, and 8, and 16. And it's really what we did when we were solving. Remember, this is the first usable network, right, up here. And that happens to be a binary 1, right? So really, we kind of did start the number line over when we're determining networks. We put it back together again when we have to put the IP address together. But when we're separated by the dashed line, we can kind of treat things off to the left like they're a separate number altogether. So all we need to do is get to where, if we were to keep counting in binary, for instance, 00011, that would be the next network, and that would be a 3. 00011 is a 3. Now, we know when we're putting the IP address together, it'll be 24, but we're not putting the IP address together now, so let's treat it like it's a 3. Well, what we need to do is get to 18. So 18, based on our new number line at the bottom, that would be 16. And we put a 0 with 8 because that would take us too high. 0 with 4 would take us too high. That would make 20, and we're looking for 18 and 19. So 16 makes 1. 2 would make 18. So that's 18. Just put a 0 there. So that gives us our network address for the 18th network. So with that network here, the first host, or set the host bits to 0 to determine the network address, and the network address would be .4. Now let's go back to the original number line to figure out the IP address. 128 plus 16 is 144. So 144 would be the network address of the 18th network, and 145 would be the interface address for the router feeding router 10, and 146 would be the next address in sequence. That's what we for router 10's serial interface. Hope that makes sense. The reason we didn't use the first address is simply because the first address was over on the right hand side routers. There would be a remote 9 in the middle here, somewhere over here, which would have 145 on its interface, and router 10 would get 146 in this design. Alright, we also need to find out about network 19. Now we know that network 19 is just simply going to be the next one in line, because this was network 18. We know that because if we were to make a little partial number line down here at the bottom, beginning where our network bits end, we know that a 1 here and a 1 here is an 18. So we're looking for a 19, so all we do is 1, 0, 0, 1, 1 is the next number in line, go up 1. That gets you a 19. 16 plus 2 is 18, plus 1 is 19, and plus it's just one more than this one, that gets us to 19. Now again, when we're actually determining the IP address, we have to put it all back together, and that gives us 128. We got to use the upper number line. 128 plus 16 is 144, plus 8 is 152. Now again, that makes sense because our increment has been 8. 8 up here in the top number line is where we've been working from. So 152 is the 19th network. We told you to find the router interface and all the host addresses. The first host address would be 001 over here, and that would be .153. So that will of course be the router, the Ethernet interface anyway. And 100.110.154 would be the second address. 011.155 would be the third. 100 would be .156, and again these are going to be the same over here on the network side. That would make the fourth. 101.157 would make the fifth. 110, remember that form, that's always the last available host, where it's all ones and a 0 at the end. That's .158. That would be the sixth and last usable host. And 111 would be the broadcast, and that's .159. And the next address would be 000, and we have to increment the network area, which would take you to 160. That would be 8 from 152. That is the next network address. That makes sense. So this would be your host range and the broadcast address of the 19th subnet. So going back, you would put .153 on the router interface here. In other words, FA0, this guy would be .153, and these guys would pick up, the 5 PCs would be .154, 155, 156, dot 157, and dot 158. You'd have a spare of dot 159. I mean, you would not have a spare because the router interface took up an address. So 159 would be the broadcast address, and you're full up here because the router interface does count as a host address. So that would be a practical example of subnetting and then applying them to PCs and a router interface based on a given scenario. Now this is a tough scenario, and these are getting more and more difficult, and we'll do some more difficult ones yet. The ones you'll have to do on your test will be of a more straightforward variety, but I want to give you some challenging ones so you're able to do an increasingly challenging array of subnetting problems, so that when you come to test time they're not intimidating to you. This is one of the hardest things you do in networking, so if you're having trouble with this, don't be afraid, don't give up, don't think necessarily this isn't for you. Just keep at it, keep trying, and it'll work out for you. We'll get plenty more examples yet, and like I said, this is one of the harder things we do, so if you get where you can do this, you're pretty much home free the rest of the way.